Good morning, here we are again. It's the physics video lecture. Physics 2A video lecture 38. I brought all this stuff to demonstrate, but then I realized I hadn't talked about calorimetry yet. So we'll see if we even get to this. However, it's all great stuff. And I also had some questions about chapter 9, number 37 and 47. So I'll go ahead and work those for starters. So first, chapter 9, problems 37 and 47. 37 and 47, yeah. Okay, these are good. And then I looked at them again and I saw these are good enough to put on a quiz. So maybe I'll put these on a future quiz and you'll have seen them worked again. So what we're looking at on 37 is the hypodermic syringe. So we've got this syringe here and a really skinny needle coming out the end, and then there's a plunger in here, and you put your thumb right there and press on it, and you squirt liquid out right there. So this is an interesting problem. It needs a little bit of judgment. We have, I'll just label this 1 and 2. So we have the 1 is right here, 2 is right here. We've got a cross-sectional area A1, minuscule cross-sectional area A2, and there is a force acting right here, pressing on this thing. And there's fluid, so we can use blue. Okay, so there's some fluid squirting out right here. There's fluid inside there. Okay, so you can think of two things. You could think that we have A1 V1 equals A2 times V2, but they only gave us the cross-sectional area of the syringe and not of the needle, so there's a problem there. We also have Bernoulli's equation, and I'll write that out. P1 plus 1/2 rho V1 squared. And you'll notice it's horizontal, so we don't have any Z component or Z axis to worry about, or Y axis. So that's P2 plus 1/2 rho V2 squared. Still not that much known. Now, we have the force here, and we have an area, area sub 1. So pressure sub 1, which is going to be greater than the atmospheric pressure, is going to be atmospheric pressure plus the force that's being imposed there divided by area sub 1. Okay, so that's the pressure plus 1/2 rho V1 squared. That's the speed of the fluid over here. Now pressure sub 2, we've done this a couple of times. It's the atmospheric pressure because that's right where it's coming out. So that's atmospheric pressure plus 1/2 density V2 squared. Now we're not going to use the continuity equation, but based on what this is, namely a very thin needle, what we can say is that V1 is much, much less than V sub 2. So we have V1 much, much less than V sub 2, and that means in this expression down here we can neglect the V1, we can just say it's small. So we get rid of that. It's not actually 0, but it's small. Okay. And then we've got atmospheric pressure on both sides, and we see that we can solve for V sub 2, which is what was asked for. And what we see is V sub 2 is going to be equal to, see, we're just equating these two expressions right there. That's all that's left. So it's going to be 2F, and then divided by rho times A1, take the square root. And the number of that, the number was given in the book and it was right. So there you have it. So that's really an excellent problem. you had to think about all these things, and also this approximation, that's not 0, it's just a lot smaller, and so we can neglect it. And there you have it. Excellent problem. So yeah, I could see putting this on a quiz or some version of this, or on a final exam for that matter. Although the final exam is just going to be a quiz, maybe a 2-problem quiz. So good, there you have it. That's one problem, and that was 37. So let's have a look at 47. 47 was the old faithful problem, and I'm just going to outline it. It's also a good quiz type of problem. So there we have this ground level. There's a geyser though, so we imagine there's some channel, and then there's a big cavern down here. This is underground, and we have water coming up here and spraying up to some great height. Okay. So we have H, I believe. Let's see how this is labeled in the book. Is it labeled at all? It's not. That's okay, I labeled it last time. So we're gonna have H above the ground and D below the ground, and yeah, we want the pressure. So let's go ahead and just call this point 1 and this point 2. Now, once the water leaves the hole here and reaches atmospheric pressure, it's essentially in free fall. So we have, I'll go ahead and first write down Bernoulli. And we know the pressure's got to be pretty great down there in order to make this happen. So we would have P sub 1 plus 1/2 rho V sub 1 squared, rho G Y sub 1, V sub 2, 1/2 rho V2 squared, rho G Y sub 2. Okay, point 2 is right at the surface. So talking about point 2 here, we have atmospheric pressure. Okay, we can call the Y sub 2 0, just make our y-axis be at 0 there, so that's gone. And we have 1/2 rho, but we know the speed because of the height of the column of water. Okay, so we would just have the standard 2gh, okay, half rho 2gh, because v squared, v squared 2gh, that type of expression. Okay. So we have the right side here. The left side, we're going to have rho g minus d, because we're down here at this great depth in that cavern down there. We're going to say the V sub 1 is negligible, similar to the prior problem, because it's the motion of the fluid down here, down low in the large area. So this is negligible again, and we can ditch that. And now we're going to get P sub 1. And I'll solve for it. Okay, we're actually done. We get the cancellation of these 2's. We're going to have P sub 1 equals, we'll take the atmospheric pressure, and then rho g negative d goes to this side and adds to this rho gh. So plus rho g h plus d, or d plus h. And this is a completely reasonable problem. This is why you never want to plug numbers into these problems until you have to, because this is essentially the pressure depth formula. So the difference between the pressure here and at the bottom is the difference in the pressure of a column of depth D plus H. It's as though you had the column up here measured from the top of the water all the way to the bottom. That's a great problem. So there you have it. And then you can plug all the numbers in you want, but only when you've figured it out like this. Okay, good. So that takes care of our review, and like I said, these are both good problems. I could put either problem on a quiz or something just like it. Okay, next. Yeah, demonstrations, I got ahead of myself a bit. Our next topic is still calorimetry. And I know you guys have a lab on that. The lab's ahead of the lecture, that happens, especially towards the end of the semester. Yeah, so let's review a bit anyway. So we have learned that there's the mechanical equivalent of heat. 1 calorie equals 4,186 joules. This is the kilocalories, also the food calorie, amount of heat, but we can convert it into universal energy unit, the joule. Then we had the idea that if thermal energy flows into something and actually out of it as well, it's flowing into this cube here, then we have Q equals MC delta T, where that's the specific heat capacity. And I asked you guys to make a little table of them in your notes. You also have a table of them in your book. 4,186 for water. 4,186 joules, kilogram degrees Celsius, C sub water. Okay. As an example, but any substance has a specific heat capacity. Okay, so in terms of calorimetry, the idea is we throw a bunch of things of different temperatures together and wait till the temperature equalizes. So I can imagine really the same picture right there, but let's say we have some object A here, and we dump it, and typically we dump it in some kind of bucket of water. It's going to write B. So if this is a hot object, I put it in water, this object's going to, cooler water, okay. This object's going to cool down, the water's going to heat up, and there's going to be an eventual equilibrium temperature. So we bring things together, and I'll put them in a box here to indicate that we're insulating the whole thing. So since we're putting it in a box and things are insulated, we're thinking there's no heat here, there's none of this Q leaving the system. So what that means is Q sub A plus, that's a Q right there, Q sub B is equal to 0. The amount of heat that leaves A enters B and nothing goes anywhere else. This is the best way to set them up, by the way. The total energy flow, heat flow, is equal to 0. And then you can just say M sub A, C sub A, T minus T sub A plus M sub B, C sub B, T minus T sub B is equal to 0. Okay, so the mass of this object, in our lab, for example, we heat up some copper, okay, and we pour it into a beaker full of water. So this would say be the mass of the copper, its specific heat that you look up, final temperature minus initial temperature. That's our delta T. Okay. Final minus initial. And then for the water, mass of the water, specific heat of the water, final temperature minus initial temperature. You do it this way, you don't have to worry about which one's hotter, which one's colder. It'll all come out in the end, and this T is the final temperature. So let's indicate that. The T here is the final temperature, that's the equilibrium temperature. And what you have now is one equation with which you can, for which you can solve, for one unknown. Okay. And for example, we know the specific heat of water. Suppose we wanted to know the specific heat of copper, because we don't know it yet. Okay. Then we measure things off carefully, measure their initial temperatures, pour the copper into the water, close it all off, and wait a while, and then we finally get this temperature here, T final. Write that down as well, and then we'd be able to calculate the unknown specific heat of copper. And different substances have different specific heats. You probably saw that if you looked it up in the tables. And that says something about their internal structure, actually. So, interesting lab, by the way. So you guys are doing some online lab of this, but the real one that we do is pretty interesting. And it's one where we're cooking water and boiling stuff and making a mess. Okay, a lot of fun. Okay, so that's calorimetry. And the simple version of the calorimetry problem, kind of thing we can do on a quiz, or we can even just say the simplest version, is if you mix water, two different waters at two different temperatures. Okay. So suppose we're mixing, this is an example now, mixing water, and we can say n sub A, or we'll just call it 1 this time, mass of one amount of water, specific heat of water, T minus T1 plus m sub 2, specific heat of water, T minus T2 equals 0. So you can set that up. You know, I could say I have a liter or a kilogram of water at 50 degrees, and I want to mix it with a half a kilogram of water at 30 degrees. What happens? That's the kind of problem. So those are easy because you can cancel this. And in a quiz situation where in class we never use a calculator, then I would give problems like this, because this 4186 that you don't want to do arithmetic with cancels, and you're just left with a simple problem here. I'm just going to write solve for T. Should probably leave some room in your notes, or maybe I'll do it for you. If you solve for T as your unknown, you've got M1 plus M2 times T equals M1 T1 plus M2 T1. So M1 T1 plus M2 T2 over M1 plus M2. So that's the kind of thing you can do here. An example. And sometimes you have more things. Okay, you have more, then you have more. You have a more complicated equation, but it's just one equation, and you can have A, B, C, D, E, F, G. If you just set it up like this with the extra objects as well, then nothing can go wrong. You just have to be careful. Because if we were to, pour all kinds of different stuff in here, the heat quanta would still be written down this way, and they would all come to this final equilibrium temperature T. So I'm going to leave it at that for the basic calorimetry, and we'll look up a homework later on. There's more to it, namely. Okay. This is the basic version. I have to talk about phases of matter for a moment here. Let me check the time. Okay, fantastic. Good, so there's our calorimetry. Our first step of calorimetry. Now let's talk about phases of matter, states of matter. You're thinking solid, liquid, gas. And plasma too, if you want to get fancy. We'll just stick with solid, liquid, gas for the moment. So states of matter solid, liquid, gas, plasma. We're just going to talk about solid, liquid, gas for the moment. Well, if you think of water that's solid, it's ice. Okay. So less than 0 degrees Celsius temperature is. You can melt it, and then once you get it hot enough, you can vaporize it. So what we're going to look at is this very common stereotypical graph that's in all the books and everywhere about what happens when you heat some water. So we'll title this here. This is a big one. You know, you can definitely fill the half width of your page. It's a big graph. Let's just title this "Add Thermal Energy to Water." Add thermal energy to water. And we're talking about the temperature in degrees Celsius, and we're adding energy here, I'll say Q, in joules. Okay. And we're going to start here. We're going to start here to the left. Actually, let's put some temperatures. So we have 100 degrees Celsius here, 50, minus 50. Okay. So we'll start, say, at minus 20 degrees Celsius, and we'll add thermal energy, and the temperature of the ice will increase. So there, we've learned we have Q is M, specific heat of ice, delta T. That's how much thermal energy it takes to raise the temperature of the ice. So you could have ice at, say, minus, I'm going to call this minus 30. Pretty cold. But you have a machine at minus 30 degrees Celsius. You just turn the dial on it and keep the temperature inside the freezer slowly increasing until it gets to 0. So you keep adding thermal energy to this ice that's at 0 degrees Celsius, and something very interesting happens, namely, it melts, but the temperature does not change. Okay? The ice melts, but the temperature stays constant. So you end up with here's our picture right here. Now you end up with a mix of water and ice that's at 0 degrees Celsius. So that's melting. And the amount of energy required, Q is M times the latent heat of fusion. So L sub F here is latent heat of fusion. And for water, so there's going to be a table in your book with all these different values. Latent heat of fusion, and that's 3.33 times 10 to the 5 joules per kilogram. Right? If you ask for what the units are, it's joules divided by mass, kilogram. And that's quite a bit. It turns out it's 3/4 the amount of heat that's required to raise this 0 degree water temperature to 100 degrees. So now we're going to add heat to the water, and actually, since I said that 3/4, we change the slope here. It'll end up about over here. Fine. Okay, that'll work. Now we're just heating the water. That's what this curve means here. Draw this fat. Maybe I should use a different color. You guys use a different color. So we're adding energy to the water. It's getting warmer. And this, of course, heating the water. MC delta T. The entire delta T is 100 degrees. And then water is boiling, and it's at atmospheric pressure, it's just going to boil away, it's going to vaporize. It's going to vaporize without changing temperature. So here we say this is vaporization, and we say the heat is equal to M latent heat of vaporization, L sub B latent heat of vaporization. Look it up in the book. Different substances have different amounts. For water, by the way, this was water. And for water here as well, all right, for water, 2.26 times 10 to the 6 joules per kilogram. Now this is a time when it's good to notice a little bit about the numbers here. Right. Suppose we have a kilogram of water. Let's say it's 1 kilogram. Okay. Then this was 3.33 times 10 to the 5 joules just to melt it, no change in temperature. And then this here was 1 kilogram, supposed to be a C right here, isn't there? Like that. 4,186 times 100. So this number here would have been 4.186 times 10 to the 5 joules. Okay. That's what I was saying. This is about 3/4 of that, right? Close enough. And we all know how much heat it takes to heat a liter of water to boiling, right? You're watching, wait for it to boil, and it doesn't. So that's a surprising amount of energy, this latent heat of fusion. Very important quantity. It plays a huge role in a lot of things. Weather and other things as well. Okay, so this graph, which you also have in your book, it's worth going over, so I've spent a lot of time on it. If you're going to do calorimetry where things are melting, solidifying, or vaporizing, you have to add these quanta here, these types of thermal energy into your calculation. Okay. You have to add these different types of thermal energy into the calculation. So we'll do an example of that, and maybe put a couple more on the homework. Yeah, so a little bit more of the calorimetry discussion. This time, let's just make up a reasonable problem. For example, we could ask, what's the ratio? Well, let's just write one down here. So another calorimetry problem. So what we're going to do is take 0.1 kilograms of ice at 0 degrees Celsius. We'll keep the problem simple. 1/10 of a kilogram at 0 degrees Celsius. And we're going to take it into, we're going to put it into 1 kilogram of water at, let's just say, 90 degrees Celsius. So here's our picture. Here's our ice. We're going to drop it into the bucket of water. Okay. We want to find the final temperature. Now, in a problem like this, you actually have to figure out whether all of the ice is even going to melt. Okay. But I chose a small enough quantity of ice that I'm sure it'll all melt. Okay. And a high enough initial temperature of the water. Otherwise, you have to figure that out, which is an extra step. But let's just talk about the energies now. So we have the thermal energy to melt the ice, and we have the thermal energy to heat. I'm going to call it the ice water. And then we have thermal energy of the original water, and those all equal 0. So to melt the ice, we have mass of ice, latent heat or fusion of ice. That's at 1/10 of a kilogram. And to heat the ice that was water, it's mass of that ice, but it's now water, specific heat of water, T final minus 0 degrees. I'm going to write it out explicitly there because the water started out at 0 degrees Celsius right after that ice melted. And then we have plus the mass of the water, specific heat of water, T minus 90 degrees Celsius. Right, T minus T water, which is 90 degrees Celsius. Equals 0. So you can solve this equation for that T, and you know, this is 90, but let me just write T water, the initial temperature of the water, because you don't want to do algebra with those 90 degrees, okay? But you solve for T, it's one equation, and then you'll find that final temperature. Okay. If you have a lot of water, for example, if we had equal masses of ice and water, and say the initial temperature was just room temperature, then what we would find is not all of that ice would even melt. Okay, you can also calculate that. No problem. Okay, so the principle always, though, is that the sum of all of these heat quanta is 0, because it's just flowing from one object into another. Good. So I'll put a calorimetry problem or two on today's homework. Let's check the time. Okay, so we will move on to heat transfer. So we're still in chapter 11, which is a major one. Okay, so heat transfer. Latent heat, excellent. Yeah, this graph is on page 357, the one I just talked about, at least a similar one. You know, it's worth talking a bit more about it. Now that we've learned the calorimetry, let's talk a little bit more about change of phase again. Just to make sure that this makes some sense. So once again, change of phase, but I'm going to make a cartoon. So for the solid, we have our block of ice. Okay. For our liquid, I guess a beaker of water is fine. And for our gas, I don't know, we'll put it in a balloon. Okay. Get some colors going on here. Okay. So we've got the liquid, and we've got the gas particles, and we've got the solid. Solid, liquid, gas, this is water. So how do we go from the solid to the liquid state? What we do is we have to add energy. And if we want to go from the liquid state to the gas state, we have to add energy, or the substance absorbs energy. So should I write add thermal energy? And point was that these are large amounts of energy because latent heats of fusion and vaporization are so great. MLF and LV. So what we don't, and this is very common of course, what we don't think about the same way in terms of energy is that if we go from gas back to liquid, we must be releasing the same amount of energy. Energy is conserved. So this is going to release energy in the same amount that it took to get into the gaseous state. So yeah, same as this amount, and the same here if we go from liquid to solid, we also release energy. And this is one that's very difficult to visualize because say we have water at 0 degrees Celsius, in the process of solidifying, turning into ice, it's going to release those 3.33 times 10 to the 5 joules per kilogram. In other words, it's going to release 3/4 of the amount of heat as it would take to bring it to a boil. Very difficult to visualize, but a very important phenomenon indeed. What happens is that, I make a little cartoon of that too. Yeah, actually here we'll do a tree. So in the winter, the citrus orchards will sometimes be either sprayed or flooded with water in order to save a citrus crop. The idea is that we've got water on the ground, okay, and let's just say T equals 0 degrees Celsius. And then we have cold air coming in, say from the mountains, and let's just make up a number. T equals -5 degrees Celsius, okay? What's warmer, 0 or -5? 0 is a higher temperature than -5, and in fact, energy will flow from the 0 degree water to the -5 degree air. It'll warm up the air, and if enough of it flows out, the water will solidify. So yeah, this little part of my cartoon is a really important one. That's how the citrus crop can be saved. Good. So that's the change of phase and energy. And again, release Q equals MLF. Release Q equals MLV. Large amounts of energy released. Okay, good. Now this actually brings us to our next topic. How does the energy get from a higher to a lower temperature object? And that is called heat transfer. How are we doing time-wise here? We'll go a few more minutes. This is actually our next topic. So here, I'll just put this on the board here. Next topic. Here's our cartoon. TH, TC. Energy flows from higher to lower temperatures, and we're going to call that heat transfer. And we want to discover the heat transfer mechanisms. I'll put some exclamation points there for you. Let's put a homework assignment up, and we'll, you know what? Can't do these demos today, we'll do them next time. Good, what about the homework problem? Let's see here. Homework in the tree. Homework number 38. We're in chapter 11. see if we can find what's good in chapter 11 here. Let's see here. So we'll just do a couple calorimetry problems. 17. Very basic. So just pouring hot objects into water at certain temperatures. $25, very basic. 17, 25. But here's an interesting one. 24. What did I say? 24? Yeah, 24. So 24 is when a car comes to a stop and the brakes get hot. So for problem 24, let me just say this. Let's use here. For problem 24, the car is moving. It's a half mass of the car v squared. Its kinetic energy is going to be converted to heat. You can do similar problems with a bullet into a steel plate and whether it melts or not. Okay, but this is the car, half mv squared, and that's going to be equal to m1 v1 squared. It's going to be m2 c2 delta t, where that's the change in temperature of your brakes. So you have to monkey around with the, yeah, they give you all, there's 4 brakes, you have to add all the 4 masses. So yeah, it's an interesting problem there too. And let's leave it at that. There's the homework, 17, 24, 25, chapter 11, and next time we're going to talk about heat transfer mechanisms. See you later.